LAN switching with redundant links. All LAN switching examples up until now were with simple LAN topologies. In the real world, every network topology uses redundant devices and links because availability is paramount for computer networks. Let's look at how switches behave when there are redundant links. Flooding broadcast, unknown unicast, and multicast, bum frames. If you recall what we have learned in the previous lesson, when a switch receives a frame, it checks the destination, MAC address against its MAC table, and if there is no matching entry, it forwards the frame out all interfaces, except the incoming interface. This process is often referred to as flooding, and the frame whose destination MAC is unknown is called an unknown unicast. The main idea here is simple. If you don't know where exactly to deliver a frame, send it out everywhere, and the recipient will eventually get it. And the receiver will likely reply back. Therefore, the switch will learn both nodes and MAC addresses and continue the future forwarding process as known unicast, not flooding the frames. Switches also flood two other types of frames. Broadcast frames. One's destined to the Ethernet broadcast address FF, FF, FFF, FFF, multicast frames. One's destined to MAC address, which starts with bits 1110. Ethernet loops, broadcast storms. If we apply this flooding logic to a switching topology with ZVO redundant links, a strange effect takes place. Let's look at the example shown in Figure 2. PC1 sends out a broadcast frame. When switch 1 receives the broadcast, it sends it out all ports, except the incoming one. Therefore, it sends a copy of the frame to switch 2 and switch 3. The same happens when the copies are received by SW2 and SW3. They see that this is a broadcast and send a copy of it out all ports, except the incoming one. In the end, the flooding of this broadcast results in the frame repeatedly rotating around the three switches indefinitely until one of them crashes because of high CPU, or one of the links gets completely congested and unusable. This effect is referred to as Ethernet loop, Layer 2 loop, or broadcast storm. Redundant topology, like Figure 2, is necessary for high availability, but switches need to prevent the bad effect of those looping broadcast frames. To stop these loops, Cisco switches use a protocol called spanning tree, STP, that causes some of the redundant links to go into a blocking state. Blocking means that the interface doesn't receive or forwards frames until network failure occurs, and the link needs to be used. LAN switching doesn't work in looped topologies, networks with redundant links, without a mechanism that breaks the topology into a loop-free one. The most widely used loop-preventing techniques are spanning tree, STP, and link aggregation, but others exist as well. Shown in Figure 3 is an example of the same network, but with a mechanism that breaks the looped topology. Note that the link between switch 2 and switch 3 is not used for frame forwarding, and therefore there is no way for the broadcast frames to loop around indefinitely. Let's check the actual status of the link between switch 2 and switch 3 from SW3's console. You can see that the interface is physically UP and line protocol is UP, but there is no actual forwarding going on. This is due to spanning tree protocol actually blocking the interface in order to prevent broadcast looping around indefinitely, as explained above. Note that the status of Fast Ethernet 0/2 is BLK, meaning blocking, and the port role is ALTN, meaning alternative. We are going to learn how spanning tree protocol works in great details in the upcoming videos.